Okay, so welcome back. Today we'll be doing tree sum. So given an integer array nums, we want to return all the triplets within the array such that all the triplets nums index I, nums index j, and nums index k all sum to 0. And note that the solution set must not contain duplicate triplets. So what does that mean? So let's look at an example that they give. Given an array such as this, -1, 0, 1, 2, -1, -4, right? We want to return an array of triplets. So triplets is just three numbers that's within the array. So this is a triplet, -1, -1, 2. So we can see it's -1, -1, and 2. So it doesn't have to be in order, but the triplets must be a subset of the original array. And what we want is that the triplets sum up to 0. So we can see that -1 plus -1 plus 2 equals to 0. Therefore, we say that this is a valid triplet. And look at the next triplet. This triplet will also sum to 0. Therefore, this is another valid triplet. And we note that the triplets cannot be duplicates of each other. So that they want that notice the solution set must not contain duplicate triplets. So this is going to be a hard part of the problem. I'm going to explain how we're going to do it. So now let's look at the first example here. Given an array of 2, 0, -1, 3, -3, -1, -3, we notice that it's not sorted. Right? The question doesn't say it's sorted, so we cannot assume so. But if you have some sum part 2 in a previous video, which you can see, we must utilize the fact that it is a sorted array such that we can solve this tree sum problem. Because let me explain how we're going to solve this tree sum using the 2-sum part 2 solution using the 2 pointers. So the first step is to be sorted, because without sorting it's going to be hard to do this question. And we know that sorting is going to be a O of n log n solution, right? So after sorting the array, we get a sorted array, right? And then we can use a 2-sum part 2 solution for this. So what we're going to do is, we're going to traverse through the array, and we're going to look at the current number. So let's look at -3 as the current number, and then we're going to look at the rest of the array, and do 2-sum part 2, 2-sum on this rest of the array. And why is that? Why will this solution work? Because if we look at -3, and then we find two numbers in the rest of the array that adds up to 3, then we can have -3 plus 3 equals to 0, and that'll be a valid triplet. So what we're trying to do is, we have three numbers, we're going to log in the number at -3, and then we're going to find two numbers that adds up. These two numbers hopefully add up to 3, such that the whole triplet will return 0. And basically, if we can find two numbers in the array that adds up to the complement of the current number, we can know that that is a valid triplet, and we can add it to a result set. So I'm going to initialize the result set as an array. Okay, and then now let's look at this. So utilizing the 2-sum part 2 solution, we know that we must keep track of 2 pointers. Let's call this left pointer and right pointer. So we're going to look at the current number, and then we're going to have 2 pointers that point to the rest of the array. So now that we have locked the numbers in place, and with the 2 pointers, we can start doing the triplet check. So we look at the current number, -3 plus -3 plus 3. So this is the position of the pointers. Okay, so this will add up to -3. Which is too small. And because it is too small, do we move the left pointer or right pointer? We should move the left pointer up, because we know that the array is sorted. So by moving the left pointer up, we know the sum is going to increase. Whereas if we move the right pointer down, we can see that the sum is going to decrease. So now we move the left pointer down, we can check again. Is -3 plus -1 plus 3 equals to 0? No, this equals to -1, which is still too small. So now we move the left pointer up. So here's the first pitfall I want you to see. If you move the left pointer up 1, we can see that it's still pointed towards a -1, right? So if we know that the left pointer is going to move and it's going to point at the same number, there's no point checking here, because we know that the combination is going to be the same, and we have already done the check. Therefore, this might result in a duplicate solution, and we don't want that, and also it causes more time complexity. So we can actually have a check in code. Whenever we move the left pointer, if it points to the same number, we can move it forward once more. So from here, we can move it once and move it twice, so that now we're pointing at 0. And then we can do the check. So is -3 plus 0 plus 3 equals to 0? In this case, yes, equals to 0. So this is our first solution. So we can add it to the result set. So be -3, 0, and 3. So this is our first solution. And now we move the left pointer up again. Because since we have already found one solution, there may be other triplets within the current array. So we want to keep on checking. So we're going to move the left pointer up. Then we're going to check. Is -3 plus 2 plus 3 equals to 0? No, it equals to 2. So we move the right pointer down. In this case, the left pointer and right pointer converge, so we know that it's gonna stop checking. We're gonna stop checking. So after that, we're gonna move on to the next number. So we'll move on to -3 and do the check here. So there's another pitfall to notice here. Look at this. We're still comparing -3 to the rest of the array. And just now during the check, we know that -3 is locked in place, right? Therefore, we know that all the triplets that starts with -3 is something that we have already checked. So if we check again the number that starts with -3, we know that the triplets are gonna be duplicate. Because we're still gonna find -3, 0, and 3, which is gonna be duplicate, and we do not want that to add to the result set. Therefore, we can add a check during the code, whereas that when we move the number up, if it's still the same number, we skip that and we continue on the check. So we skip the second -3 and move on to -1, and we do the triplet check again. So we have the two pointers, -1 and 3 here, and we check, is -1 plus 1, -1 plus 3, does this equal to 0? No, in this case it equals to 1, which is too big. Therefore, we move the right pointer down. And then we can check, is -1 plus -1 plus 2, does this equal to 0? In this case, yes, it equals to 0. Therefore, we found our next solution. So this will be -1, -1, and 2. Awesome. Right, and then we move the left pointer up. So we move it here, and then we check, is -1 plus 0 plus 2, does this equal to 0? No, this case it adds up to 1, which is too big. Therefore, we move the right pointer down, and since they converge, we can stop checking for -1. So then we move on. So we check -1 here. And see, this is the same case here, right? Because we have already checked all the triplets that starts with -1, there isn't any point of checking the -1 again. Therefore, we can skip here, and we continue on to 0. And then we check here, and because this is the only triplet, the left pointer and right pointer, we know that 0 plus 2 plus 3 equals to 5, which is too big. Then we move it down. The right pointer converts the left pointer, and then we have done checking the whole array, and this will just return us these two triplets, which are the two valid triplets for this entire array. Now let's look at another example. So this is the example given in the Leetcode question itself. We're gonna check, because we're gonna sort it first. So this takes O of n log n. So now after sorting, we're gonna do the check. So we're gonna look at the first number and then find the triplet. So we know that -4 is gonna be locked in place while we do the check. So we look at the two pointers and we're gonna check, is -4 plus -1 plus 2 equals to 0? No, it equals to -3, which is too small. Because it's too small, we move the left pointer up. And here's another case where we can see that since the left pointer is still gonna point the same number as we move it, we can continue onwards. So is -4 plus 0 plus 2 equals to 0? No, equals to -2, which is too small. So we move the left pointer up. Then we do the same check. Is -4 plus 1 plus 2? No, it equals to -1. Too small. Therefore, we move the pointer up. And the pointers has converged, so we know we can stop the check. Now, then we're gonna move it forward. We're gonna check -1, and we'll do the triplet test. So now -1 will be locked in place, and we're gonna do the two pointers. Is -1 plus -1 plus 2 equals to 0? Yes. So we have found our first valid triplet within this array. So we'll add it to the index result set. So -1, -1, 2 is our first array. Then because we have found the first one, we move the left pointer up, and then we check. Is -1 plus 0 plus 2? This equals to 1. And because it's too big, we move the right pointer down, and then we check. Is -1 plus -1 plus 1, is -1 plus 0, because 0 is the index here, right? So is -1 plus 0 plus 1, this equals to 0. So we have found our next solution. So this will be -1 and 0 and 1, and then we can continue and move the left pointer up. And because it has converged, we can stop checking, and then we can continue. So here we can see that we move on to -1, but because -1 and -1 is going to be the same number, we have found all the triplets that starts with -1. So there's no point checking again all the triplets that starts with -1. Therefore, we can just skip this -1 and move on to 0. And in this case, we check that is there any number triplets that is valid. So it's going to be 0, 1, and 2. This is going to be 3, which is too big. Therefore, move the right pointer down. It has converged, so we can stop the check. And therefore, we know that the only two valid triplets in this array will be these two triplets. So we can see that this is also the same answer that they give in the example. Yeah. So now let's look at how we can code it up. So we need a result set. So we initialize it to an empty array. So this is where we're going to store all our valid triplets. And next, we're going to iterate through the array, right? So we're going to do for I in range, the length of nums. Okay. So before that, we must actually do nums.sort. So this actually sorts the array such that we can use the 2 pointers approach for this question. And we can see that the current number equals to nums index I. And here's the first check. Remember we said that if we are checking -1 and we move to -1 again, we don't want to check the same triplet because we know that we have already found all the triplets for -1. So we can add a check here. If I is greater than 0 and the previous number equals to the current number, we can just continue the search. Alright. So here is the actual starting of the triplet check. So we can initialize left pointer equals to I plus 1, because we can see here that the left pointer is going to always be one index ahead of the current number we are checking. And the right pointer is always going to be the length of nums minus 1. So it's going to be the end of the array. And then here we can check, well, LP is less than RP. We want to check the tree sum, right? So the tree sum is going to be the nums at LP plus the nums at RP plus the current number. And if the tree sum is less than 0, so if it's too small, remember we must up the LP, right? So we'll increase LP by 1. Else if the tree sum is bigger than 0, that means it's too big. Therefore, we must decrement RP by 1. And if tree sum equals to 0, that means we have found our first valid triplet. We can just do result.append the array of the triplets. So we have the number, we have the num in LP, and the number at RP, right? And since we have found the valid triplet, we must continue checking, right? Because there may be other triplets. So we can do LP plus equals to 1. And here's the other condition we must check. If we ever see that LP is still the same number, we can have to continue skipping on forward, right? So we can do while the nums at LP minus 1 equals to the number at LP, and we can just, here is double equals, we can just LP plus equals to 1. So we continue on the search. And here must be additional condition while LP is less than RP, because there may be a case where LP is duplicate, right? So they keep on going forward until it passes RP, and in that case we just want to stop checking. So hopefully if there's no bugs in this program, we can just return result, pray for the best. And so silly mistake here should be number, the nums, because num is the current number, so nums is the actual array. So let's press this, and here there's another error here, so it should be nums instead of num. And let's hope that it works now. Okay, and so if we submit this problem, it will run. Okay, I beat 69% of the code. So this runs in O of n squared time complexity. Why? Because we know that sorting costs O of n log n, right? But then we have to, for each number, we are doing the check of the 2 sum. And we know the check of 2 sum will take O of n time. So if we have to go through each array, each item in the array, and do O of n operation, it will be n times O of n, which is just O of n squared. And because the sorting cost O of n log n, right, this will be O of n squared plus n O of n log n. And because n squared is going to be dominant over n log n, so the final solution will just be O of n squared. So I hope that this has helped you. It's a pretty hard problem, but if you understand 2-sum part 2 using the 2 pointers approach and try to break it down, you will be able to solve this question. So thank you for watching.